Hello everybody, welcome to my YouTube channel, Theoretical Physics with Mark Weitzman. I'm going to continue with the third video in the series on QFT review blog video. This is based on Z's textbook, QFT in a nutshell. And we're going to try and explain repulsion and attraction. Scalar, vector, and tensor. So this is part C on tensor. We've already done the scalar case and the electromagnetism case. So now we're going to do a tensor. So gravity is a tensor theory, and a massive spin 2 particle has 5 degrees of freedom. Just remember your usual angular momentum formula of 2s plus 1, in this case equals 2 times 2 plus 1 equals 5. That's the number of, so we have, thus we will have 5 polarization tensors. And they're going to have 2 indices now on each tensor. And A goes to 1 up to 5. So now we have a these are of course symmetric, because gravity is a symmetric theory, symmetric tensor theory. Another way of thinking about this is we have a tensor theory in space-time of 4 dimensions. We have 16 components, but the anti-symmetric part of the tensor will have 6 components, and that's just the electromagnetic field and the electric field and the magnetic field. So an anti-symmetric tensor is just a spin 1. And then we're going to also have the trace of the tensor, and we're going to get rid of that. The trace would correspond to a scalar part of the gravitational force, and that's spin 0. We're going to get rid of that. And so we're going to end up with, and then we're going to have a current conservation condition. So let me show how this works out. So we have current conservation. And so that's that. And then we're going to have tracelessness. Not sure that's a word, but so we're going to have that our this is going to be G mu nu epsilon A mu nu K equals 0. So we start out with 10 symmetric components. Then we subtract four components from the current conservation condition. And then we subtract one component from the zero trace condition. So we have 10 minus 4 minus 1 equals 5. It's the same as we had before, just reasoning from spin. Now we'll also have a normalization condition. So this is one condition, two condition, three condition. There are different ways you can do this. It doesn't really matter. But that's our normalization condition. So as we need to determine our propagator, and so we need to determine the polarization frames. So the purpose of the rest of this video, for the most part, is to evaluate this object. And so the only objects are at our disposal the only objects available are the metric and the propagation vector, wave vector. And we can also we'll work more often, just conveniently, to work with G mu nu, which has the same definition as it was defined previously. So these are and K mu. So these are our objects, and now we're going to work through what seemed like some hairy equations. They're really not. They're not that difficult at all, actually. And so what follows is this is basically the solution of exercise 1.5.1 on page 39 of Z's QFT, second edition, nutshell book. And using symmetry arguments, Z gives you things like it should be invariant under if we switch the indices like this, and so on. Using these kind of arguments, Z gives us a head start by giving us the most general form, and there's basically 5 terms. So we're going to have the sum over A Our first term will be a coefficient multiplied by g mu nu g lambda sigma. Second term, so obviously this satisfies that symmetry argument. A g mu lambda g nu sigma. Oops. And if you study these for a while, you'll become convinced that these are the only possibilities. So that's two terms. The third term with a coefficient of c. Fourth term. This is the most complicated one. And then finally our last term. So now we're going to use the definition. By the way, this implies that k mu g mu nu equals 0. Since if we multiply k mu times the first term, it just raises the index and we get k nu. Then k mu upper and lower just is the magnitude of the energy momentum vector, which is just k squared, which is m squared. And so we're going to get k nu minus k nu, which is equal to 0. And then our conditions that I labeled before, now I'm going to label them A, B, C. We're going to get k mu, the sum over A, now this is like more complicated. This, the first term over here times this is already 0. So we don't need to sum over all A, and we don't need the second thing, but clearly this will still be 0 if this times this, if this kills this, because we'll need it in this form. And then we have our tracelessness condition. Then we have our normalization condition. Okay, so now it's just a matter of substituting, plugging and chugging and so on. So using A in our original equation, in equation 1, this is going to be equation 1. I'm going to number the equations and I'll put the conditions that I use on the left side. So I'm going to get 0 is equal to, because we're basically multiplying this equation over here by k mu. So we're going to multiply So we get 0 is equal to, okay, well, I'm going to multiply. I'm just going to use condition A over here. So 0 k mu sum over A epsilon A mu nu k epsilon A lambda sigma k. Now what does this do? Let me put this whole thing in a box. Okay, so if I multiply this by k mu, I know that k mu g mu nu is equal to 0, so that kills term A. And term B is also killed. The first term, k mu g mu lambda and k mu g mu sigma, are both killed. So A and B are killed right away. And we're left with C. Now, okay, so the first term in C is killed because, again, k mu g mu lambda equals 0. The second term has a k mu upper and k mu lower. That's just m squared. So we're going to get C m squared k nu g lambda sigma. And now I'm going to get plus D. Oh, let me write it. Plus, I'm going to get D. And again, the k mu is m squared. So I'm going to get D times m squared k lambda g nu sigma plus, and again I'm going to get m squared k sigma g nu lambda. Now k mu g mu lambda is killed here and is killed here. So that gives me the D term. And then I'm going to get plus E. K mu is m squared. So I'm going to get E m squared k nu k lambda. Oops. Now let's multiply equation 1 by k nu. And this we'll call this equation 2. So I'm going to get 0 is equal to, when I multiply by k nu is m squared, so I'm going to get C m to the 4th g nu sigma plus, now when I multiply by k nu, again, k nu g nu sigma is killed and k nu g nu lambda is killed. So there's no D term. I'm just going to get plus E, and k nu is m squared. So E m to the 4th k lambda. Okay. I think I left out E k nu k lambda k sigma. So this is k lambda k sigma. Okay. Now Now let's multiply 2 by k lambda. We get equation 3. So now we get 0 equals okay, so this should be a lambda. Let me just make sure. Multiply k nu, yeah, g lambda sigma. Okay. So when I multiply this by k lambda, this term gets killed. I'm just left with e m to the 6th k sigma. Now this implies E equals 0 because we can work in a rest frame where K 0 equals M in rest frame. And all the other Ki equals 0, so that will just give us E m to the 6th times, if we take the 0 component, we'll get another M. So this just implies E equals 0. So we've gotten rid of one of the terms. Now, using 2 again, since now we have E equals 0, we're going to get C equals 0, because that, again, I can work in a rest frame. In rest frame, Ki equals 0, and G11 is just equal to G11 equals -1. So we just want to look at some components where this term is gone. We just want some components where this is non-zero. Then we can say C equals 0. Remember, G11 is the metric minus K1, and in the rest frame, Ki equals 0. So does that. Now, using what we have, multiply equation 1 by k lambda. So this is our equation 1, and we get 0 equals, remember E and C are already 0. So we get 0 equals D. When we multiply k lambda is m squared, so we get D m to the 4th G nu sigma. And again, k lambda times G nu lambda. Remember, G is symmetric, so that's the same thing as k lambda times G lambda nu. That gets killed to 0. So this implies, same arguments as before, that D equals 0. So we've gotten rid of 3 of our most general terms. That's good. So now let's go back and let's write equation 4. This is where we're at now. Sum over A, epsilon mu nu A, K, epsilon lambda sigma A, K is equal to A, G mu nu, G lambda sigma, plus B, G mu lambda, G nu sigma, minus G mu sigma, G nu lambda. Okay, so we've only got 2 terms in our polarization sum, which is good. And we just have to determine, we have to determine exactly what A and B are. Excuse me for a second. Okay, so now we're going to multiply 4 by g mu nu and use condition B. Remember, condition B is the tracelessness condition. So now we get 0 is equal to, because when I multiply g mu nu times g mu nu ak, that's 0. And so on the other side, we're going to get a g mu nu g lambda sigma plus b g mu nu g mu lambda g nu sigma plus, I don't know why I wrote a minus sign there. I don't think that's correct. It should have been plus g mu sigma g nu lambda. Okay. Now let's evaluate some of these terms. This will be equation 6. Let's call this 5. G mu nu g mu lambda g nu sigma is equal to so what we're doing is we're just lowering the index. We're raising the mu index to a new index. So del nu lambda minus k nu k lambda over m squared times g nu sigma minus k nu k sigma over m squared. Okay. Now this is equal to the first multiplication. We just substitute lambda for nu. And if you haven't had a general relativity course, this exercise gives you good practice in index manipulation. Now I get minus k lambda going out here, k lambda, k sigma over m squared minus k sigma k lambda over m squared plus, I'm going to have m to the fourth, but k nu is m squared. So I'm going to get plus k lambda k sigma over m squared. So these two terms cancel. And our final result is this is just the definition of g lambda sigma. Okay. And then the next thing we want to calculate, so we calculated this. Calculate this term over here. Now we got to calculate these terms. So let's do, they're actually the same by symmetry, but g mu nu okay. Let me think for a second. So I just want to calculate let me just look at what I had previously done. Oh, okay. Oops, sorry. So I didn't do this term first. I actually did this term right over here, and this term is the same. Now I want to do this term over here. So G mu nu, this is equal to G mu nu now the metric, this is going to be just del nu nu, which is going to be equal to 4 minus, then I'm going to have k mu over m squared, which is just equal to 1. So it's 4 minus 1 equals 3. Okay. So using 5 again, so substituting, I get 0 is equal to we evaluated this part over here. The first part of the A is 3. 0 is equal to 3A G lambda sigma plus 2B. I stated that these two terms are the same. You can work them out and see, or just look at the symmetry argument. Plus 2B G seemed like I calculated the whole thing. Okay, so it's 2B. Then I have to put in this term here. Boy, I hate these tablets. I have 2B. We evaluated this. Should be G lambda sigma okay, it's G lambda sigma. It comes out to that. Okay, I'm sorry. 2B G lambda sigma. And this implies that 3A plus 2B equals 0, or A equal minus 2/3 B. So we just have the normalization condition. So using C and 5 in 4, we're going to get 1, because of normalization we're going to substitute 1, 2 for mu nu and 1, 2 for lambda sigma. So I'm going to get 1 is equal to the sum over A, epsilon 1, 2 A, K, epsilon 1, 2 A, K, and this is equal to minus 2/3 B G12 G12 plus B G11, G22, plus G12, G21. Okay. Now in the rest frame, again, always go to the rest frame in relativity. K0 is equal to M, Ki equals 0, G22 equal to G11 equals minus 1, and G12 equals 0. So substituting in there, we end up getting 1 equals B. And this implies A equals minus 2/3. We're almost done. So our polarization sum in the propagator okay, good. Now, the propagator itself, I'll write that down again. This polarization sum. So, gravity is as we've been working, is a spin-2 field. And so it has to couple to a 2-index source. And we usually call this the stress energy tensor. T mu nu, which is conserved and symmetric. Conserved just means the partial mu of T mu nu x equals 0, or K mu T mu nu K equals 0. Okay. Now usually our general result for W, complete analogy with the scalar and vector cases, the interaction of lumps of stress energy is given by W of T. T here is the stress energy tensor, not the time as it was before. Now, using the conservation condition, We may, as an EM case, replace by G mu nu. And we can specialize to lumps of energy density, which is T00. So we set all indices to 0. And we get W, let's say T00, minus 1/2 the integral of d4k, 2 pi to the 4th, T00k star, get 1 plus 1 minus 2/3, k squared plus m squared minus I epsilon, T00k. That's our final answer. And since 1 plus 1 minus 2/3 is greater than 0, we're good. The potential energy and gravity is attractive. Now there's some caveats on here with respect to the non-zero mass and a few other things, and Z talks about them in the book, but he doesn't get to it much later. But the end result is still the same. So I hope you got a feel. Don't worry too much about the details in all these calculations, but you get a feel of why a vector theory might be different than a scalar or a tensor theory, and where the sign change comes from. And it's kind of interesting how QFT can sort of explain both the inverse square law and whether it's attractive or repulsive. So thank you very much for watching. I'll see you next time. Bye-bye.